Hi guys, hope all is well, and today we are starting 10.5 on tangents. Now just a reminder, there are a lot of theorems in 10.3, 10.5, and 10.7. This is our next chunk of lessons that we're currently doing. Make sure you're staying up on them. Don't forget you have a textbook. I don't refer to it often, but you can look in the textbook if you want to see some of these examples or see worked out examples. And also just, look at these theorems a little bit more in depth. I know they're on my notes. You can also find some more videos online for this. Make sure you're asking me if you need help checking your homeworks, doing your lesson checks. And, if you get behind or you need help with something, just feel free to let me know. Otherwise, just keep up the good work. So we are discussing in 10.5 tangents. So we talked about tangents earlier in the year, and a tangent line is a line that only touches a circle once at something called a point of tangency. So Theorem 10.10 says, in a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So what does this mean? And I know it sounds super complicated, but it's really not that. It just says that the way we know a line is tangent to a circle is if, when we take the radius, it is perpendicular to the point of tangency. So if it's perpendicular, then we know that that line would be tangent. So for example, if you look at the picture up at the top right, line L would be tangent to circle S because it's ST is perpendicular from, to at the point of tangency. Okay? So how can we use this? So the first way we can use this is to prove something is tangent. So it says JL is a radius, and you know that's a radius from looking at it, of circle J. So JL is a radius, and it is 8. Determine whether KL is tangent to the circle. So how do we prove whether something is tangent? If you go by the previous theorem, if something is tangent, the radius will be perpendicular to the point of tangency. And I apologize for my chicken scratch of writing, so I'm sorry about that. I'm doing the best I can. The math tends to be a little bit better than the actual writing. But the way we prove something is tangent is we show that, there is, so is there a perpendicular there? Is there a right angle? How do we prove that something's a right angle? We use Pythagorean theorem. Now here's the issue. You always have to check with questions like this to see what they give you. They give you that one side is 8, that's JL. They give you KL is 15. But if you notice, they do not give me the whole piece of JK. They only give me the piece that is outside the circle is 9, that I just highlighted in red. But we know that this inner piece is the radius. The radius is 8. So the whole thing is 8 plus 9, so the entire segment JK is actually 17, okay? So what are we trying to prove? We're trying to prove that our triangle is a right triangle, and that triangle has sides of 17, 8, and 15. So which one would be the hypotenuse? 17 squared. We want to know, is that equal to 15 squared plus 8 squared. If it is, we have a right triangle, we have a perpendicular, which means we have a tangent. 17 squared is 289. Is that equal to 225 plus 64? Luckily, yes, it is. They are equal. So yes, because it is perpendicular. Okay, think back to your proofs. 90-degree angle told me perpendicular. So if it was not equal, then you would just say no. We would know that KL is not tangent to the circle. Okay, our next problem says, so we have another try problem. You can go do that. Remember, your try problems are on your worked out notes and on your blank notes. But let's go on to our next example. Example 2 says find the value of x. Lines that appear to be tangent are. So there's only one line that could be tangent here, and that would be, my point of tangency would be J. So if it appears to be tangent, it means that there would have to, by Theorem 10.10, there would have to be a right angle there. So when they say lines that appear to be tangent are, they're telling you there's a right angle at point J, or at angle J, I'm sorry. Okay? So we want to find the value of x knowing that we have a tangent, or knowing that we have a right triangle. So what are our side lengths? Our side lengths of a right triangle are x, 12, and if you do the math, just like the last one, x plus 8. So let's use Pythagorean theorem. So we have our hypotenuse, x plus 8 squared, is equal to a squared plus b squared, x squared plus 12 squared. Make sure you are putting x plus 8 in parentheses. That is your hypotenuse. That needs to be squared. Now, what does it mean? What is x plus 8 times x plus 8? You're going to have to FOIL this. So, x plus 8 times x plus 8 equals x squared plus 12 squared. X plus 8 times x plus 8. So first, outer, inner, last is equal to x squared plus, and 12 squared is just 144. Now I'm going to combine like terms on the left side. X squared plus, in this case it would be 16x plus 64 equals x squared plus 144. Now normally, I would say you would have to factor this, get one side equal to 0. But if you notice, this one actually works out nicely because you see there's an x squared on both sides. What happens when you have the same thing on both sides, guys? Hopefully you're thinking that it would cancel. So my x squareds would cancel, and I'm left with 16x plus 64 equals 144, and this we absolutely know how to solve. We would get 16x equals 80, so x just equals 5. And this would be our final answer. So when they tell me lines that appear to be tangent are, they're telling us that at that angle, at that point of tangency, that angle would be 90. So we end up with a right triangle. Okay? Let's keep going. Theorem 10.11 says, if two segments from the same exterior point are tangent to the circle, then they are congruent. Now, I like to call this one the ice cream cone, because if you look, it looks like an ice cream cone. Oh, that was terrible tracing on my end, but it does look like an ice cream cone. We have our scoop of ice cream and our ice cream. So I tend to call this one the ice cream cone. If we were in class, it may actually be funny. But of course, this is me trying to be funny and failing. But what we have here is, what this is saying is, if we have two tangent segments that meet at the same point outside the circle. So in the case of our diagram, they would meet at point B. So both of these segments, one is tangent at point A, and one is tangent at point C. They both meet at B. That means that if they both are tangent to the circle and meet at the same point, that the two segments are congruent to one another. Okay, very actual simple theorem in this case, and let's see how it's used. It says, find the value of x, lines that appear to be tangent are. So that means at point A and point C, we have tangent points of tangency, but that also makes AB and CB tangent. So if both of these segments, AB and CB, are tangent to the circle, meet at the same point B, that means that AB is congruent to CB, that they are congruent to each other. So once they are congruent to each other, what can I do? I can very simply set them equal. X plus 15 equals 2x minus 5. So we get x equals 20. Okay? Again, our ice cream cone, they're equal. Whenever you think of your ice cream cone, think equal. So they are congruent, or they are equal. Okay? You don't want, just think your ice cream cone, if you have it in your hand, you want your ice cream to sit perfectly on top. So both sides of the cone are going to be equal for you. Okay? And you can do your try problem number 3. And we're going to move into our last little example in this section. And it has to do with tangents, so it kind of fits in. circumscribed polygons is, or are, a polygon is circumscribed about a circle. So circumscribed just means around a circle. So a polygon is around a circle if every side of the polygon is tangent to the circle. So what does this mean? So if I have a circle, and of course it's not a perfect circle, so I have my circle, and it's basically saying that a polygon is circumscribed about a circle if every side of the polygon is tangent to the circle. So say we're talking about a triangle. In order for this triangle to be circumscribed about this circle perfectly, each side has to be tangent to the circle. Okay? If you look at this, what actually ends up happening is, if you look, we actually get 3 different occurrences of what I was calling our ice cream cone. Okay? Because we have segments, like what I just outlined in orange, that ends up, both of those segments are tangent to the circle and meet at the same exterior point. What I outlined in green, both of those segments are tangent to the circle and meet at the same exterior point. What I outlined in blue, both of my blue segments that I just outlined meet at the same exterior point and are tangent to the circle. So we actually end up getting 3 different cases of our last theorem. Okay, so of our last theorem, where we know those chords are congruent. So let's do an example. This example says, a graphic designer is giving directions to create a larger version of a triangular logo shown. If triangle ABC is circumscribed about the circle. So if the triangle ABC is circumscribed about a circle, you know each side is tangent to the circle. We want to find the perimeter. Okay? So what do we know? So we know if each side is tangent, we know that what I've outlined in green, those 2 points both meet at point B, those 2 segments, EB and FB, both meet at point B and are tangent, which means those 2 are congruent. Okay? We also know that AE and segment DA meet at point A and are tangent to the circle. So they are congruent. And lastly, we know that if DC and FC, I'm going to use a different color so you guys can see that. So DC and FC, I'm going to change that again. Let's see. What color don't I have on there? We'll do blue. So DC and FC are also tangent to the circle and meet at point C. So they are congruent. And we need to find the perimeter, which means we need all of the pieces of this puzzle. So let's start at the top in the red. So we know that AD is congruent to AE. So if AD is 8, AE is 8. Okay? Which is perfect because that tells me my entire side AB is 8 plus 7, which is 15. Okay? We also know the entire bottom piece is 10. So I have 2 sides, I need the third side. But here's my issue. I do not know what DC is or CF. But I do know that CB, the entire thing CB, is 10. And if I look, EB is congruent to FB. So if EB is 7, FB is 7. If the whole thing is 10 and FB is 7, that means that whatever is left is 10 minus 7, which is 3. So that means that CF has to be 10 minus 7, which is 3. If CF is 3, that's congruent to CD, which is also 3, which tells me my entire last side of this, which I'll put in gray, has to be 3 plus 8, which is 11. Okay? So my perimeter is going to be 11 plus 15 plus 10. If you do that math, we're going to get 26 plus 10, so our perimeter is 36 feet. If you looked at this a little bit differently, that is fine. But just like I said in the last one, we know that what I have in blue. So these pieces are congruent by the snow cone, right? These pieces are congruent by my snow cone, my past theorem, because they're both tangent and they meet at the same exterior point. And then these two are both congruent because they're both tangent and meet at the same exterior point, which is what we use in our example here. Okay? And this is our last example for this section. Make sure you go back, watch the notes a few times if you have to, complete your lesson check, and then complete your homework the next class period. Okay? A lot of theorems, try to keep them straight. Maybe make yourself flashcards, or just, keep going over the examples to help yourself. Good job today, guys. Make sure you ask me if you have any questions.